In this session, we are going to talk about 11th Physics, Chapter number 4, Laws of Motion, Part 8. First point is couple and its torque. In the discussion of the torque given above, we had considered rotation of the body about a fixed axis and due to single force. In real life, quite often we apply two equal and opposite forces acting along different lines of action in order to cause rotation. Common illustrations are turning a bicycle handle, turning the steering wheel, opening a common water tap, opening the lid of bottle, that is rotation type, etc. Such a pair of forces consisting of two forces of equal magnitude acting in opposite directions along different lines of action is called a couple. It is used to realize a purely rotational motion. Moment of couple or rotational effect of a couple is called a torque. It may be noted that in the discussion of rotation of a body about a fixed axis due to a single force, there is a reaction force at the fixed axis. Hence, for rotation, one always needs two forces acting in opposite direction along different lines of action. Couple and its torque can be explained in animation as like this.
Couple. Two equal unlike parallel forces whose lines of action are not the same constitute a couple. The effect of couple is to produce rotation. Examples for couple. When we turn a doorknob, we produce a couple on the knob. When we wind a watch, we produce a couple on the winding key with our fingers. When we use a screwdriver, we produce a couple on its head. When we turn top, we produce a couple on its head. While spinning a ball or a top, we produce a couple. Moment of couple. The moment or torque of a couple is the product of either force or the perpendicular distance between the force, or moment of the couple is the vector sum of the torques produced by two forces, individuals, about a fixed point. Let F and minus F be the forces acting on a body simultaneously at points A and B. As the lines of action of these forces do not coincide, we say that a couple is acting on the body. The net force acting on the body is F net is equal to F minus F is equal to 0. That is, the net force exerted by a couple is 0. Let R1 and R2 be the position vectors of points A and B about an axis passing through a fixed point O. The torque produced by the force at A about O is tau 1 is equal to R1 cross F. Its turning effect is in anticlockwise positive direction, and the direction of torque is normally to the plane and outwards. The torque produced by the force at B about O is tau 2 is equal to R2 cross F. Its turning effect is clockwise, negative direction, and its direction is normal to the plane and inwards. Net torque produced by the couple about the axis passing through the point O is tau is equal to tau 1 plus tau 2. That implies tau is equal to R1 cross F minus R2 cross F. That implies tau is equal to R1 plus R2 cross F. That implies tau is equal to D cross F. The magnitude of the torque is tau is equal to Fd. Note, the moment of given couple is constant about any point. Summary. Torque. It is defined as the turning effect of a force about a fixed point and is measured as the product of magnitude of force and the perpendicular distance of line of action of the force from the fixed point. The magnitude of moment of the force or torque of the force F about the point O is given by tau is equal to Fr sine theta. Torque of the force F about a point O in vector from is given by tau is equal to R cross F. Couple. Two equal unlike parallel forces whose lines of action are not the same constitute a couple.
Torque or moment of couple. Figure 4.8 shows a couple consisting of two forces and of equal magnitude and opposite directions acting along different lines of action separated by a distance r. Corresponding position vectors should now be defined with reference to the lines of action of forces. Position vector of any point on the line of action of force F from the line of action of force is 2. Similarly, the position vector of any point on the line of action of force from the line of action of force F is torque or moment of the couple is then given mathematically as line of action of force. This is a figure for torque of a couple, which is a figure 4.8. Here all symbols have as usual their meanings. In the discussion of the torque given above, we had considered rotation of body about a fixed axis and due to a single force. In real life, quite often we apply two equal and opposite forces acting along different lines of action in order to cause rotation. Common illustrations are turning a bicycle handle, turning a steering wheel, opening a common water tap, opening a lid of a bottle, rotation type, etc. Such a pair of forces consisting of two forces of equal magnitude acting in opposite directions along different lines of action is called couple. It is used to realize purely rotational motion. Moment of couple or rotational effect of couple is called torque. It may be noted that in the discussion of rotation of a body about a fixed axis due to single force, there is a reaction force at the fixed distance or fixed axis. Hence, for rotation, one always needs two forces acting in opposite directions along different lines of action. It is clearly shows that the torque corresponding to given couple, the moment of a given couple is constant. That is, it is independent of the points of the application of forces or position of the axis of rotation, but depends only upon magnitude of either of force and the separation between their lines of action. The direction of moment of couple can be obtained by using vector formula of the torque or by using the right hand thumb rule. Next point is moment of a force. First, vector τ is equal to vector r cross vector f. Second, vector τ depends upon the axis of rotation and the point of application of the force. Third, it can produce translational acceleration. Also, if the axis of rotation is not fixed or if friction is not enough. 4. Its rotational effect can be balanced by a proper single force or by proper couple. Next, moment of couple. First, vector τ is equal to vector r12 cross vector f2. Second, vector τ depends upon the two forces, that is, it is independent of the axis of rotation or the points of application of forces. 3. Does not produce any translational acceleration but produces only rotational or angular acceleration. 4. Its rotational effect can be balanced only by another couple of equal and opposite torque. Next point is mechanical equilibrium. As a consequence of Newton's second law, the momentum of a system is constant in the absence of an external unbalanced force. This state is also called mechanical equilibrium. As particle is said to be in mechanical equilibrium if no net force is acting upon it. For a system of bodies to be in mechanical equilibrium, the net force acting on any part of the system should be 0. In other words, velocity or linear momentum of all parts of the system must be constant or 0 for the system to be in mechanical equilibrium. Also, there is no acceleration in any part of the system. Mathematically, sum of vector f is equal to 0 for any part of the system for mechanical equilibrium. Thank you.